So moving on with the portions, we'll first take a look at some of the basic concepts regarding the filters that we are supposed to learn. So you would have already learned about filters in your previous semesters or different subjects like analog circuits and things like that. So you have learned about filters like low pass, high pass, band pass, and band reject or band stop. So these are the four types of filters that you would have mostly learned. Let's take a look at what each of these filters are. So you know, low pass filter, there will be one cutoff frequency, that is omega c. So this will be like from 0 to some high values, like let's take an example of pi. This is omega and this is hd of omega, thus making this a graph of the frequency response. So this graph is called frequency response because it is a response of the system that is plotted with respect to the frequency, which is omega over here. So you have a cutoff frequency called omega c out here, and since it is a low pass filter, it would mean all frequencies below this will be passed through and the others will be rejected. So it would be a bit more of a graph like this, where this would be your cutoff frequency. So this is a graph for a low pass filter. In comparison, let us take a look at what high pass filter would be. Again, a high pass filter would be having a cutoff frequency omega c, and all frequencies below it will be rejected and the ones above it will be passed through. So this could be treated as a response of a high pass filter, where this belongs to pi, and this is the cutoff frequency. Similarly, for the next filter we have learned is band pass filter. So unlike what we have drawn earlier in this particular graph here, there will be a small difference, that is, there will be two cutoff frequencies. So when we have to draw this particular graph for band reject or band stop filter, band pass or band stop or band reject filter, we'll have two cutoff frequencies. So omega c1 is here and omega c2 is here. So band pass would be all frequencies between these cutoff frequencies will be passed through. So I'm having a graph like this. All frequencies between this will be passed through and the others will be rejected. So this can be treated as an example of a band pass filter. Similarly, when we talk about band stop filter, again there would be a cutoff frequency as shown in this graph. Two cutoff frequencies, omega c1 and omega c2, and it would be rejecting the frequencies in that band of frequencies and the rest will be passed through. So this can be treated as the graphs of different filters that we have learned, the low pass, high pass, band pass and band stop filters, which you had learned in your previous subjects. As we move along, the next big difference that we have to understand is in the terms of analog filters and digital filters. So right now it must be clear that since our subject is DSP, we are mostly concentrating on digital filters, and analog filters are the ones that you had designed in your previous semesters, which involve components like resistors, capacitors, etc. So we'll take a look at the different kinds of filters or the major differences between the analog filter and digital filter at a later point of time. But let me remind you something, that our topic of concern is digital filter, and we'll be learning two kinds of digital filters now. One is FIR filter and other is IIR filter. So FIR stands for finite impulse response, finite impulse response, and IIR stands for infinite impulse response. So in this particular module, we'll be dealing with FIR filter, and in the fourth module, we'll be dealing with IAR filter. Considering a general aspect as shown in the diagram over here, this is a basic model of signals and system. You have the input signal and output signal, and you have a system that works on the input signal to produce the output. So generally, input can be treated as the impulse and the output generated will be the response. And how this response will be generated from the impulses depend upon the special property of this system known as impulse response. This is something that we had already discussed earlier regarding impulse response. And what is the relevance of this impulse response? And this impulse response is something that defines the characteristic of a system. So when we talk about FIR filter specifically, like I mentioned before, it stands for finite impulse response. So what it basically means is that the property of the system, which is called infinite response or impulse response, not infinite response, impulse response, will be finite in nature. Or what I mean to say is that if it has got an impulse response like h of n, it can be defined by finite terms. This can be a concept of FIR filter. We'll look into this at a later point of time because we have to specifically go into problems, and definitely we'll understand this. So the topic that I wanted to explain right now is what is FIR filter in general. So FIR filter is like any other system which works on an input impulse signal to create an output response depending upon the system property known as impulse response. And if that impulse response is finite in nature, it will be called finite impulse response filter. It has got its own set of advantages and disadvantages, and in comparison with IAR filter, which we'll be looking at a later point of time. For designing of an FIR filter, there are two methods basically. One is Fourier series method and other is window method. Now, Fourier series method has got a certain disadvantages which is rectified by Windows method. Essentially, if you look at your syllabus, maybe Windows method is the only defined one, but understanding Fourier series method will give you a better concept of window method. So we'll move on to the Fourier series method first of solving this particular FIR filter design. Before beginning with the actual design of a Fourier using Fourier series technique, let us get the concept of types of filters for the FIR filter design. Now we have already looked into a basic concept of this, but for our specific application we need to adapt that graph into a suitable one for this particular scheme. So now, since our signals are periodic over a period of 2 pi in the frequency domain, we consider a span of 2 pi, and specifically since we are considering a span of 2 pi, it will be existing from minus pi to plus pi. So if we are to plot a graph of the low pass filter, so we have pi and minus pi here. Now for a low pass filter, we drew a version where there was a single cutoff frequency omega c, and I'm drawing one my graph over here I would be using for an ideal filter. Now ideal filter, it can be a low pass, it can be a high pass, it can be a band pass, or it can be band reject. So what I'm drawing here is an ideal filter for all these kind. So if I am to draw the graph for a low pass filter, it would look like this. We draw the graph like this, we come down and it goes to plus pi. So this would be the graph for a low pass filter in the ideal concept based on what we have learned previously also. So this is something that you would have drawn earlier in your circuit subjects as a response similar to an ideal one. Similarly, if you look at the other half, that is from 0 to minus pi, there should be an equivalent version over here which is equivalent in the mirror reflection scheme likewise. So if you draw that graph, the graph will be like this. Okay, and this is 0. So this would be the graph for a low pass filter. So this is the x-axis, which is the frequency. This is the y-axis, which is the frequency response, and this is the graph that you get. Now if I want to write what is the HD of omega for a low pass filter, I would write it as 1. Since it is an ideal filter, I will write it as 1 for minus pi, or let's call it minus omega c less than or equal to omega less than or equal to omega c, and 0 for pi less than or equal to omega less than minus omega c, minus pi less than or equal to omega less than or equal to minus omega c, and omega c greater than or equal to greater than omega greater than or equal to pi. So this would be the response for a low pass filter. Similarly, if you look over here, the graph for a high pass filter, a ideal high pass filter, would be as follows. So you will be having the cutoff frequency omega c over here. This would be the ideal response, and for a 1/2 of this section. So similarly, when you plot it on the negative half, you will have minus omega c. So again, the concept would be like a mirror image, and this would be the graph, and this amplitude is 1. So for a high pass filter, HD of omega will be equal to 1 for minus pi less than or equal to omega less than or equal to minus omega c, and omega c less than or equal to omega less than or equal to pi, and it will be equal to 0 for minus pi by minus omega c less than omega c. So this would be the graph for the high pass filter. So when we draw for a band pass filter, since it is a band filter, you'll be having two cutoff frequencies, omega c1 and omega c2, and the ideal frequency response will be like this. All the components between the cutoff frequencies omega c1 and c2 will be passed through, and others will be rejected. Similarly, you'll be having two cutoff frequencies. Here it is minus pi, minus omega c2 and minus omega c1, and all the filters here, all the values here will be passed through, and others will be rejected. So when you look at it, the response for a band pass filter will be as follows. HD of omega will be equal to 1 for minus omega c2 less than or equal to omega less than or equal to minus omega c1, and omega c1 less than or equal to omega less than or equal to omega c2, and it will be equal to 0 for minus pi less than or equal to omega less than minus omega c2, and minus omega c1 less than omega c1, and omega c1 less than omega less than or equal to plus pi. Similarly, when you look at the band stop filter, you'll be getting a graph like this. The filter will be rejecting components in this particular band, omega c1, omega c2, and minus omega c1, minus omega c2. So the equation would be 1 for the interval specified here, and 0 for the interval specified here. So this is an example of the different kinds of filters. I repeat, the different kind of ideal filter which will be used for FIR filter design.